Hello everyone, welcome to this video. In this video, we are going to learn about ARMAX using OpenMathAI. So, let's get started. What is ARMAX? ARMAX, or AutoRegressive Moving Average with Exogenous Inputs, is a supervised dynamic time series model used to predict the future output of a system. Unlike traditional regression models, which mainly use current input values, ARMAX considers previous outputs, external inputs, and previous prediction errors. The autoregressive part uses previous output values to represent the memory of the system. The exogenous input part uses external variables that influence the system, while the moving average part uses previous prediction errors to improve future predictions. During prediction, ARMAX combines the previous output values, delayed external inputs, and previous residual errors using the coefficients learned during training. This allows the model to represent both the dynamic behavior of the system and the effect of disturbances. Imagine we want to predict the output of an industrial process controlled by a valve. The process output does not change immediately when the valve command changes. It also depends on the previous process outputs, previous valve commands, inlet load disturbances, and unmeasured process noise. We will use a dynamic process dataset for the ARMAX model. This dataset contains 800 time series samples. The external input features are valve command and inlet load, and the target output is process output. The dataset also contains a time step value for maintaining the correct sequence of observations. During training, ARMAX learns a relationship between the current process output, the two previous process outputs, the delayed valve commands, and the previous inlet load value. It also estimates the effect of previous prediction errors internally. Once the model is trained, OpenMathAI uses the learned ARMAX parameters and the recent system values to predict the future process output for new valve commands and inlet load conditions without retraining the model. The dataset must remain in time order and should not be randomly shuffled because ARMAX depends on previous observations. So, let's get started. Open OpenMathAI. In this demonstration, we use a valve control process output prediction dataset for the ARMAX model. Click Create New Project. Enter the project name as Valve Control Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There is a free columns. First one is column. It's tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's okay, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the ARMAX model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is train from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of R-squared residuals and residuals diagram. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format. ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.